Hello students. Today we're going to talk about more basic shapes in geometry. But I want to go back and ask you, what is geometry? Well, let's look at the word first. Metry means to measure. And geo is the prefix for earth. So there's a lot of classes in school that start with geo. What are some other classes that start with geo? Geography. Geometry is this one. How about geology? There's a lot of classes that start with geo because geo is earth. So the word geometry means measuring the earth. In this class, when I say what is geometry, I want you to think of it as a language. So if we open up the geometry book, there'll be a lot of vocabulary. And there's a lot of symbols, so it has its own notation and its own writing. So when I say what's geometry, I want you guys to say it is a language used to talk about shapes and their relationship. Geometry is a language used to talk about shapes and their relationships. That's why when you open a geometry book, there's a lot of shapes. There's also a lot of vocabulary because it's a language. And we talk not just about shapes, but the relationship between the shapes. So let's do a little review. What's the most basic shape in geometry? And we said earlier that a point has no dimension. It's infinitely small. You can't measure it. But we can make shapes out of points that do have a dimension. They have a length. So what basic shapes can be made out of points in one dimension? Good. Make a line. What's part of a line? Yeah, that's the one we talked about yesterday, a line segment. How about, so line segments have two endpoints. Any other shapes made in one dimension? What if we had half of a line? What would that look like? That would have an endpoint, and then it would continue in one direction, but not two directions. It would only go off one direction. That shape is called a ray. Okay, so we have lines, and then part of lines are line segments. And then half of a line, the fancy word is a ray. Rays we didn't talk about before. So rays have, the most important point on a ray is this end point or this starting point. I'm going to call it R. And then the next most important point on a ray is telling you which direction it's going in. So this point over here is not important, that point. The points along the ray are what's important. So I could put a letter, should I call that point A? Why not? So if I wanted to talk about this ray, I would say this ray is named ray RA. The symbol here means ray, and it is the set of points that start with R and they go forever in the direction of A. If there was another point on here, it would be overkill. We could also name this ray RY. We would not use all 3 letters because we only need 2 and we don't want overkill. So ray, R, Y. If I was talking about ray, YA, that would be super different. Or ray, AR, that would be super different. It would not be the same set of points. If I was going from A out to R and was a ray, it would be the points over here on this side. That's not what I want. I want the points that are represented. Oh shoot, I clicked the wrong thing. That's fun. We get to review. No, I can't click on it. Okay, no problem. So we don't want that ray. All right, what else? So those are our shapes that can be made out of 1 dimension. What shapes can we make out of 2 dimensions? Well, a lot of the shapes you learned when you were little were 2-dimensional. So what are some shapes you learned when you were little? If we put line segments together, what shapes can we make? 1 line segment next to another line segment, next to another line segment, next to another line segment. What shape is that? Kind of a quadrilateral. You did squares. Squares are made of line segments. We did triangles. We did circles. All of these are 2-dimensional, right? We did rectangles. Remember rhombuses? Kind of look like diamonds. They have all 4 sides that are the same, congruent sides. So these are called our kind of our plane figures, 2-dimensional. What's even more simple than this? What do these polygons all have? Not the circle is weird. What do they all have inside of them? If we can answer this one. What shape is created with 2 rays and a common endpoint? So we have a ray with this endpoint right here. Call it, here's ray ER. And we have another ray with a common endpoint, and it's going that way. Ray ET. 2 rays with a common endpoint, that could be a line, right? That's what some of you were thinking, I know. So we have ray ER and we have ray ET. 2 rays, the common endpoint is E. It's kind of the starting point for each one. What else could we make with 2 rays and a common endpoint? Good. Make something like that. What shape is that? Good. That shape is an angle. So let's talk about a word. We talked about collinear before. So we have 3 points all in a line. Those points could be said to be collinear. So points, if we're talking about vocabulary, right? Points T, E, and R are collinear. I'm speaking another language now. I'm speaking geometry. Points T, E, and R are collinear. Another thing we could talk about is the relationship between these 2 rays. The ray that goes out this way and the ray that goes out this way. So when you have this special situation where you have 2 rays that start with the same letter, but go exactly in opposite directions. So you have ray ER and ray ET. If you have a situation where you have both of those rays, those are called opposite rays. So the pair ray ER and ray ET are opposite rays. They have the same common endpoint. They both start with E, but they go on the picture in opposite directions. So that's another vocabulary word. Both of these vocabulary words refer to the relationship between shapes. So the relationship between point T, point E, and point R is that they're all on the same line. The relationship between this ray ER and this ray ET is that they are opposite rays. Let's go back to this one. What shape is this? Good, it's an angle. The way we draw the angle symbol is like this. It looks like a less than, but it's flat on the bottom. If I want to say, hey, look at this picture and I want you to look for angle V, would you know where on my page angle V was? Yeah, your brain would see V and then would look over here and you see an angle. So this is named angle V. We can name angles with just that point at the corner, just that common vertex between the two rays, the common endpoint. We can also put some extra letters on here like L and Q. I could also use 3 letters to name the angle. So I could put the angle symbol and then I could put L, V, Q. If I say, hey, look at my paper, can you find angle LVQ? You'd be like, yes, Miss Bliss. If I start at L and I go to start at L, can't do that. I start at L and I go to V and I go to Q, I have drawn that set of points. I've drawn this side that's a ray, I've drawn the point that they have in common, and I've drawn the other ray. If you screwed up the order and you went from L to Q to V, that would not be drawing the angle. That would be bad. That would not be the same angle. That would be a shape from L to Q to V. Did I trace the angle? No, I'm all heck of in the middle over here. So that's no good. Don't do that. So the order matters. You could have it the other way. You could have it angle QVL, as long as that V, that vertex is in the middle, you're okay. Again, if you try to go from L to Q to V, that would be screwed up and you would not be drawing the angle that you're thinking of. There are other types of angles. So this one happened to be an angle that looked like the angle symbol. But if you have other angles, like, I don't know, let's say you have one that looks like that. Maybe it's perfectly kind of square in the corner. If I say I want to look at angle R, how I would draw the symbol would still be exactly the same way. This is angle R. Whereas angle R on the paper, it's over here. Happens to be a right angle. So what can we do with angles? Can we measure them? If I draw an angle right here, can you tell me how big it is? Can you put a number with this shape, or can we just name it? Lines we can just name. We can't measure a line. We can't measure a point. Can we measure angles? Yeah, we can measure angles. So the answer is yes. The way we measure angles is thinking about if it was a circle, how much of the circle would it be? So if I'm starting here and I want to get over to here, how much have I traveled around a circle? Okay, that's kind of how we measure it, and we measure it in degrees. How many degrees around the circle did I go? Did I go all the way around 360, or did I just travel part of that way inside across through the angle? So we measure angles with a protractor. So I'm going to draw an angle over here, and we're going to grab this protractor and put it on and see if we can use the numbers on the protractor to figure out how big the angle is. Okay, so we'll call this angle T. And I can, like I said, I can go over here and grab this protractor. This is called the protractor postulate, and I can slap it straight up onto that angle. I'm just going to slap the protractor onto the angle. And I'm going to look at the numbers on the protractor, and that's going to help me figure out how big this angle is. So let's use the outside numbers. We can use either one. I'm going to cheat slightly by making this a little more accurate. So I'm going to look at the numbers on the outside of the protractor. Notice how they go from 0, 20, 30, 40, 50, 60, 70, 80, 90, all the way over to 180. So 180 is half of the whole circle. So we only need half the circle if we're measuring this kind of angle. So this looks like this ray is hitting the protractor. If we're using the top numbers, this looks like 95 up here. 95. And then this ray is hitting the protractor, and I'm going to call that 155. So the question is, how big, what number should go with angle T? Angle T is a shape. Happens to be an angle. The measure of angle T is a number. And I want to know what the measure of angle T is. What number goes with this size shape, or this shape that has a vertex here. The way to do that is I can use the numbers and I can subtract them. I can do 155 minus 95. And why do I have the absolute value? I have the absolute value because I don't want any negative answers out. So I'm going to do on my calculator 155 minus 95. And I get exactly 60. That means it is 60 degrees out of the 360 degrees on a circle. To get from here up through the angle across to the other side is 60 degrees. This is called the protractor postulate. You can slap a protractor onto an angle, and you can use the numbers on the protractor to tell you how big the angle is. Now, if you are better at using a protractor, you would not slap it right there. What you would do is you would adjust it so that the protractor lines up with the bottom. So the bottom of the protractor lines up with one of your sides. And what that does is it makes it easier. You no longer have to do a subtraction problem because one of your numbers is 0. Okay, so let me adjust this just a little bit more. Okay, so if you place your protractor properly, you're going to put the vertex down at the middle. Some protractors have a hole in them, some don't. And then you are going to line up one of the sides of the angle with the bottom of the protractor. What that does is that tells you, okay, I'm going to start at 0. Now in this one, am I going to use the inside numbers or the outside numbers? I'm going to use the inside numbers because I'm going to go 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50, 60 degrees. So this would be 0 out here, and this would be 60 up here. And now if you set up the protractor right, all you have to do is look at this number, 60, because 60 minus 0 is 60. So another way to do it is to place your protractor properly and just look at the number on there. That's the protractor postulate. Tomorrow we'll talk about the different types of angles. There are 4. See if you can think about what they are. All right, one type of algebra problem we can do with angles is this type. So in geometry, this is a whole language. We can read it and we can make sense of the problem. When you're doing work in geometry class, it's always good to draw the figures and then mark them up. So I would copy that onto my paper, and then I would take all of this information and I'd put it into my figure. So what does this say? It says given M angle. Okay, oops, that stands for measure. Given the measure of angle JML is 80 degrees. So I'm going to stop. That's all I'm going to read. I know that the measure of angle JML is 80 degrees. I'm going to jump to my figure and I'm going to try to find where is angle JML right there. So the next thing I'm going to do is I'm going to mark my figure. From the measure to get from J to M to L through the middle, the measure of that angle is 80 degrees. Maybe I'll write it really small. It takes 80 degrees out of the whole circle to get from here to here. All right, and I also know it's also given that the measure of angle KML is 33 degrees. That makes sense. It's a lot smaller, isn't it? Okay, so the big one across is 80 degrees, and this little one in here is 33 degrees to get from there to there. So the question is, what is the measure of angle JMK? The measure of angle JMK. That's my question mark. That's what I want to find out. That's what I want to know. And some of you can just look at these numbers and go for it. Like, oh, I see, you have to subtract. What numbers do you have to subtract? You have the total, which is 80, and you have 33, which is this part, and we want to find this part, right? So someone said, oh, Miss Bliss, just do 80 minus 33. That's correct. Good job. If you want to look fancy and show the geometry, you would write it like this. You would say that the measure of angle JML, which is the big one, is equal to the measure of angle JMK plus the measure of angle KML. And this is called the angle addition postulate. Angle addition postulate. It says that the little angles add up together to make the big angle. And then from this, if we want to translate this into algebra, we would say, okay, we know that the measure of angle JML is 80 by some substitution. And we don't know what the measure of angle JMK is. You have a choice. You could change this to an X, or you could rewrite this. And do we know the measure of angle KML? Yep, it's 33. And you could just subtract 33 on both sides. And it's going to give you your answer. So 80 minus 33 is 47. Okay, what did I say about getting X? Is that the answer in geometry? Sometimes, sometimes not, usually not. So we have to go and answer this question. What is the measure of angle JMK? JMK is 47. So the measure of angle JMK is 47 degrees. That's it. That's how you do some math problems with angles and the angle addition postulate. Be good, do your homework, and I will see you next time. Bye, students.